I will talk about one of the buildings that we designed in Dubai. Before, I have a few slides on the company. Koltay Facades started in 2011, 15 years ago in Dubai. We opened the Singapore office 10 years ago, and up to date we worked on many projects, around 200 actually. A few of them are here. We worked with several famous architects all over the world, and we managed to put interesting buildings in every continent. Some of the buildings that you may recognize is Museum of the Future. Currently we are working on a very interesting cast glass building in Misk in Saudi Arabia. And that's about the introduction, and let's get going on Skyview. So Skyview is a project that was actually the design started, I believe, 2007, 2008. Then it stopped for the economic downturn. And then it continued right after. So the original design is by SOM, and then Canadian company, local architects took over, and we worked with them. The building is hotel and residential with the Sky Bridge feature and quite a few interesting tourist attractions on the top. This is the side that you see from Sheikh Zayed Road side, the busy road side. Here you see panoramic elevators. Panoramic elevators that can take up the visitors directly to the observation deck. The observation deck is located in the nose of the building. Here. You see it's a busy intersection in Dubai near Burj Khalifa. The project is this one. Here the two towers are still separated. They got married together by the Sky Bridge. It took about 6 weeks to lift the Sky Bridge to its position. And that's exactly where our story starts for the Sky Slide, because the building was already constructed about this much when we got the notification from the client that they would like to include another feature in it. We worked on the building since schematic stage. Typical unitized system curtain walling with some interesting wavy floor plate design. You see these on this zoomed detail how the spandrel actually departs from the building and creates kind of a ribbon in front of the balconies. That will be interesting later. The building is clad with stainless steel, and the next image shows the process of elevating the Sky Bridge. You can imagine that these floors that are accepting the Sky Bridge here are full of steelwork, like really big steelwork that this part will get attached to when it's elevated into place. And that's when we got the notification about the Sky Slide. Yeah, great idea. We got this design as well, design intent, which we didn't find exactly buildable. So we got the chance to work on it a little bit, which was an interesting task because my background is architecture. A couple of my other colleagues are architectural backgrounds, but we are doing engineering. Facade engineering is the most visual aspect of all kinds of engineering because you get to see what you engineer, not like foundations or the elevator shafts, let's say. So it's a very nice thing to do. But in this task, we actually got the opportunity to fully design even the architectural look and aesthetics of the structure as well. So that was the basic idea. This area was already dedicated to the observation deck, which was a glass-floored walking area of the building. And then the idea was to take the people and let them slide down from the 53rd floor to the 52nd floor. Knowing that this slide doesn't take too long, and knowing that if you start from the building and enter back in the building, basically your experience is almost unnoticeable. It's 1 or 2 seconds. Our aim was to extend this experience. So the first idea we had is, why don't we just simplify the shape as well, so it's easier to build, less risk of injury in those bends, and have a glass box sticking out of the building, another glass box sticking out on the 52nd floor, and connect them with a straight slide. So the experience starts with looking around in the glass box and then arriving to a glass platform. The structure there in between the 2 floors was already quite busy with steel structure. So the structure engineer managed to fit another piece of steel for the landing platform and for the arrival platform. Also, we had the idea to shape it architecturally in a way that also visually and psychologically extends your journey. As you slide down, you have this feeling to basically go through the glass by using this inclined piece at the end. For the chute itself, we wanted to use the longest possible piece of glass, which was 14 meters at the time, and it fitted the purpose well because the high distance in between the 2 floors justified the use of the glass. So this would be the launching platform where you enter the slide and start your journey. We had other funny ideas, like using a ball pit at the end of the slide. The client at the end didn't like this idea, unfortunately. They were afraid of hygienic issues, although it would have been even more playful. Actually, this end of the glass, this inclined piece of the glass, became the most spectacular and most photographed part of the project, which gave us a lesson to learn for next projects. Instagrammability is very important, especially these days. The only thing I would probably change on this project, if I did it one more time, to extend this platform even more, to allow more people to take pictures in this position, because this became the most famous part of the project. A little bit about the design of it. So when we started working on it, the difficulty was that there's basically no code for glass slides at an elevation. We could find some building codes for playground structures and for water slides, but nothing for glass structures or anything that would be applicable for us. So the first question, what would be the inclination of such a structure? What we did, we specified, designed a temporary structure which was adjustable, and the main contractor built it on site. So we had our team and their team and the architect and client and everyone, and we just got our friends and kids and everyone to experiment the slide and record the experience. We had 3 adjustments, 24, 26 and 28 degrees, to experiment out what would be the best inclination. Of course, the actual experience depends on not only the inclination but also the fraction coefficient of the surfaces. But that was kind of given because our intention was to use a mat to slide to avoid the problems with having different clothing or different surfaces to touch the slide, and also to use a protective film on the glass. So that protective transparent film is something that the operator has to replace time to time. Otherwise, the wind loads were pretty typical. These are the 15 glass panels for the 2 glass boxes. The 2 glass boxes are quite standard, typical construction with point fixing. The glass chute is something interesting. It got created from 4 pieces of glass, and it's all held together by structural sealant. So it was done in a SIDAC factory in Germany. The structural sealant work was done over there as well. This is one of the big glass pieces in their factory. You see here the edge of the glass. So that's the side of the chute. This side is a 4-layer laminate with an additional 3 layers at the bottom. So around this line, somewhere here, there's actually, oh no, sorry, it's on the top because it's upside down. So here you see this, here you see the line, yeah? That's 7-layer laminates here. This is the bottom of the slide, and the top of this glass is the 4 layers. So those additional layers are there to create a glass shelf, and the floor of the slide, the floor of the chute, is sitting on that glass shelf. So basically, the structural sealant and the interlayer action keeps it structurally together. Apart from this, we designed some metal fixtures for post-breakage redundancy, but that's actually secondary, and it's not structurally working at a normal state of the slide. So the other interesting design question was the safety factors. What safety factor to use? And these safety factors that you see on the screen are something that we basically set up ourselves with after consultation with some other industry players. But basically it's completely arbitrary, and it's way above the normal expectations, and it's not just because of the risk of personal injury. It's also the reputation loss that could come from having a piece of broken glass, having to stop the operation for half a year or maybe longer to wait for the glass to be replaced, or maybe the whole chute to be replaced by the operator. So we wanted to avoid any such risk. Of course, it's glass, so if someone wants to break it, they will break it, but it shouldn't happen as an accident. Other interesting issues with the engineering, just modeling the whole thing, modeling the whole glass chute piece was quite a challenge. Not sure about if there's any progress with the structural softwares, finite element softwares since then. But when we did the engineering, basically there was even a limitation in the number of bricks that you can use for the solid meshing. It was 250,000, which was not sufficient for modeling the whole thing. Basically, the brick proportion should be close to 1:1, but if you use the limited number of bricks, we ended up with some bricks 1:100 ratio, which is not really ideal. So we had consultation with the software manufacturer, the software developers. We ended up having some local models to model separately certain critical parts of the structure, and then we had the global model. The global model, at the end, we used a surface mesh, and we extruded that to use for modeling. The structural sealant itself is a very interesting question for engineering and modeling. Sealant has a hyperelastic hyperelastic behavior. So there are some models that can be used, and some advice that can be taken with manufacturers. So we worked closely with Dow Corning at the end. They had quite advanced technical advice at the time of the engineering, and ended up modeling using these hyperelastic models and modeling the structural sealant as springs. So here you see the detail where the floor of the glass slide sits on the glass shelf of the side of the chute, and this would be the top of the chute itself. Another interesting question is the interlayer. The interlayer has different behavior at different temperatures. Dubai is an extremely hot climate, but how hot really is, that's a question. So how hot can glass become exposed to the sun? We were thinking of using double glazing for the bottom, the sliding surface of the slide, but not for the top or the side walls, and just the rooftop of the slide, which is the most exposed to direct sun. What could be the material temperature of it, and how does the SGP interlayer behave in that temperature? SGP was marketed at the time as quite heat resistant, or something that has better behavior at higher temperatures than PVB, and that's true. But at what temperature? They had tests up to like 50 degrees, 60 degrees. We ended up doing an in-house experiment. So we had some glass samples in our office in the roof, and for the summer months in Dubai, we measured 3 times a day the surface temperature of those materials, and as you can see, it's relatively within a range. We ended up using 80 degrees material temperature for the engineering. At 80 degree, none of the interlayers provides good attachment and coupling behavior anymore. So for the roof, we had to have another piece of steel at the bottom of the roof to keep the dead load. Also, structural sealant has a very different stiffness and behavior than the steel attachments. This slide shows the release of the loads at the rotules. These rotules are the secondary structural system of the boot, and this is how they look like. And this is the big bracket that supports the whole slide. So this big slide is one piece of structure, basically behaving like a simple beam with support on top and bottom. These big brackets are providing those supports. There was a very interesting, long testing week, multiple sessions of testings for components and to check if everything behaves as we expected. These are some of different attachments and different parts of the slides. During these testings, it's really nice to have a good collaborative environment with the testing facility people and with the contractor, because none of us knows what you can really expect. So maybe something happens which was not what we expected, and that's an interesting thing to happen. Something that we should discover together, and we should look at to see what caused it, why we didn't expect that, and what to do to solve it. Here you see. It's not standard testing anymore. The standard testing is to test it until something fails. And once the first piece of glass is failing, the test is basically over. But it's always nice to continue and break one more piece of glass and one more piece of glass to see how much additional redundancy is left in the connection. Not because you are expecting all the 6 layers to be broken, but because you want to know what fails first and what does it do after, yeah, and how much extra capacity you had in your calculations, and how does it compare with what you experienced during testing. So that's when the test was completed and we were standing on the broken glass, and then we kept on continuing. This is the bottom surface of the slide, the floor of the slide. It was designed for 500 kilograms per square meter as a maximum load. Obviously, there's no person being 500 kg, but let's say there is. So it's super safe. But as you can see, even with broken glass, 1.6 tons was the maximum actual capacity of the assembly. And when I mentioned that things happen that you don't expect, this is one of them. So this is the inclined roof of a piece of the inclined roof of the slide, and as I mentioned, we cannot expect that the interlayer would hold it together. So we had to have some small piece of metals to take the dead load and stop the layers from sliding in case the temperature is so high that the interlayer starts to behave like butter and the pieces of glasses start to slide on each other. And then we wanted to test this, but the testing equipment couldn't handle it. Unfortunately, it got as it pushed the glass. So these are 2 hydraulic jacks pushing the glass. But as it pushed it, the glass just kept popping out. So by next day, they had to put this big beam here, basically, to force the glass down. And this is not really what anyone expected, this type of behavior. But you have to be inventive during testing, and that's the joy of it. And at one point, it passed all the tests, and the glass arrived in a nice big box to site. It came together with a carrier frame, and that carrier frame, which was 2 tons on its own, had to be lifted together because it kept the slide from any deformation, unexpected deformation during the lifting. That's a last load test on site, and then they started lifting it. So that's the carrier case. Oops. And it went up and up and up. It went up with 2 special cranes that was designed and procured just for this reason, to lift the slide chute up and to allow replacement of the side chute or any other big glass pieces during the operation of the building. So each of these cranes are 7.5 tons, and together they can lift the slide. It was a very slow process lifting it, and you see the normal BMU cradle there. There was a person in that cradle watching the process and making sure that everything is going smooth. It was a slow process, but not super slow. So it was basically 1 day to elevate the slide up to its position, which is about 200 meters above the ground. And here they started fixing it into position. It took another close to 2 weeks to actually fine-tune and align the slide in its final position. The big bracket and some more construction images, and that's it. That's the completed slide. It's not curved. It's just because I took the panoramic image with the camera moving, but it's a straight slide. So if you visit Dubai, obviously not right now, but hopefully very soon. I'm very, very hopeful that it's very, very soon. Then please come and enjoy. Thank you very much.